等到下个，然后我妈给你吃个饭，然后你一个人是骂人家就是我也有时候完了在跟多少讨论，然后
So I'm talking to the guy who did like this in the past, and he's a server for videos. And so I'm not guarantees on Monday, but they'll definitely.
All right, let's go ahead and get started. So hopefully you guys all know that Lab 1 is due. Still a few hours. Hopefully you're not just thinking of starting right now, but good luck if you are. Please make sure that you do your Git, follow the submission instructions, make sure you've done the right tagging so that we can see your changes. Is there a question? It does push it, right? It creates the tag and pushes it. Yeah.
It only works on like a Linux environment. Just go to GitHub and make sure that you have a tag for last one.
And for some reason, like this is the first time we've done this, and for some reason it's causing you terrible pain or something. We don't want, this isn't the preferred solution, but like you could send us an email at 11:55 and say the script is broken, it won't work. Here's like the commit ID or something. Like you can't get it to work. It should work, but just like we understand that the environments are a little weird. So, all right, so. We're going to post problem set 2 today. So problem set 2 is not due for I think 3 or 4 weeks. So you still the idea with problem set 2 is it's meant to be sort of some problems that go along with this series of lectures that we're doing to prepare you for the quiz. It's a little bit different than maybe some of you are used to in terms of problem sets. Just from the point of view of like turning in homeworks and other things, we would prefer not to have a ton of like weekly problem sets. So it's just like. But it's a little bit of a comprehensive problem set that's supposed to be preparation for quiz 1. It's probably okay to put it off if you have the time to put it off until the week before quiz 1. But on the other hand, you might like look at it now and just to kind of get a feel for the problems. And some of the problems, like there's one problem on ER design that you might you could probably do now, and it might be pressure in your mind, or you might want to wait until just before the quiz and use it as review. So it should be posted later tonight. We're also posting Lab 2, and Lab 2 is due I think a week and a half. So okay. And then finally, for those of you who are doing the problem sets, the final project, we've got a lot of stuff going on this week. For a lot of you, those of you doing the final projects, just your list of team members is due on Wednesday. If you don't have a list of team members, feel free to just turn in a sheet with one name on it, your name. And if you have an idea for a project, feel free to put a couple sentences of what you think you might want to work on in your project, but don't feel obligated to do that. I'll be meeting with all the teams over the next couple of weeks. I'll set up 15-minute, a Google Doc where you guys can sign up for 15-minute times to come in and talk with us, just to, so you can bounce some ideas off of us and we can give you some quick feedback about whether it seems like the right direction or not. I'll probably schedule that a little bit before and a little bit after the project proposals are due, so that you guys have a little bit of time to think about what you might want to do, and then we can give you some feedback once you've had some time to kind of percolate your project proposal. All right, so any questions about any of that stuff? I know it's a lot. Okay, so let's get to the lecture. So today we're going to talk a little bit about cost estimation and some more about access methods. In particular, we're going to talk about hash-based access methods and a little bit about disk-based hash access methods. So if you remember last time, we kind of got through talking about this iterator model thing. So how the executor works as iterators, And then we talked just briefly about some simple access methods. In particular, we talked about heap files, and we saw a very high-level picture of B trees. We'll probably talk today or maybe at the beginning of class next time a little bit more detail about B trees and specifically these B plus tree things that database systems use. So we're kind of still in this access method storage system part of the lectures. I thought I'm going to do something a little bit differently this year, which is that in the next lecture, we're going to talk about kind of a different way of designing database systems, namely something called column-oriented database systems, which is sort of a new idea that's come up in the last 5 to 10 years as to how you should build a certain class of database systems. It's just a different way of structuring the data inside of the database, just to, because I think it's kind of nice to see that even though there's this sort of classic textbook way of building a database system, that there actually are different ways you might lay out the internals of a database depending on your workload. So next lecture will be a little bit of a diversion from this plan, and then we'll come back to talking about buffer management and lock transactions and optimization and all that kind of stuff. Okay, so today we're going to talk about specifically about two things, cost estimation and then access methods some more. Okay, so the idea with cost estimation is, so we saw last time how we could build up this query plan, we can instantiate the physical operators in that query plan with different kinds of implementations, like different join algorithms and different access methods like B trees and B files. But what we need in order to build up sort of query optimization is a way to reason about the cost of a given plan so that the query optimizer can compare different plans to figure out which one is better. So we're going to spend the first part of today really just talking about how we can think about the cost of a plan. And then we're going to use that to sort of start to think about the costs of these different access methods. So once we've thought something about what, we've sort of formulated a way to think about costs, then we can think about which access method is better for which setting. Okay, so cost estimation is this idea that, well, I give you a query plan and I want to come up with a number, which is the cost. Okay, intuitively, you can think of cost as being like times in milliseconds or something to run the query plan. Although when the query optimizer generates these costs, and you saw that with the little Postgres demo I did last time, it has these cost numbers attached to it that don't necessarily correspond to anything in the real world. They're just some numbers. But you want them to be sort of relative, like a higher cost plan should be slower to run, and you'd hope that it's proportional to time, although making it actually be proportional to time is might be a little bit tricky because these cost units are sort of depends. The cost is going to depend on some function of the amount of I/O that the thing has to do, and some function of the number of instructions it has to run, and the exact correspondence to real time may be a little squishy. All right, but at some level, right, cost is going to be sort of equal to the amount of CPU. Cost is sort of proportional anyway to the amount of CPU plus the amount of I/O. Okay, where I/O is usually we would think of as being the disk time, but it could be network or other costs as well. Okay, so this is sort of when we think about the cost of a plan, we want to kind of think about how much CPU cost is it and how much I/O cost. All right, so when we're thinking about the sort of relative magnitudes of these costs, it's always useful to kind of go back to our, have a model in our heads of how expensive these things are relative to each other. Okay, like how much does CPU, how does the amount of time taken to execute one instruction compare to the time to, read some number of bytes from the disk? Right, so let's just go back to sort of basic computer systems and review that just so we're all on the same page. So let's talk about CPU time. So how long does the CPU take to run like one instruction in ballpark? I'm talking like super ballpark, but. So a nanosecond is a pretty good number, right? Because these CPUs run at like, a couple of gigahertz, approximately 1 gigahertz, right? So if it's running at 1 gigahertz, it's running a billion instructions per second, so it's running 1 nanosecond per instruction, right? So 1 gigahertz approximately is equal to 1 billion instructions per second, 1 nanosecond. And how many, does anybody have a ballpark estimate of like, suppose you're, I don't know, evaluating like how many instructions do you think it would take to evaluate a, I don't know, given a tuple in SimpleDB to like evaluate a predicate on it? Does anybody have a ballpark estimate of how many instructions that might be? It's probably kind of hard to ballpark. Is it one instruction? What's that? Yeah, I mean, that's sort of, mine would be somewhere between 100 to 1,000. I don't know, it's a little bit hard to actually estimate this. If you actually start thinking about it, it does quite a few things, right? It's a bunch of function calls. You know, it has to pick apart as this array in memory, and it has to pick out the fields. Because SimpleDB is fixed length fields, it can sort of do direct offsetting to tuples, so maybe it's a little faster because it can do some arithmetic to, you know, find the offset of a given field in a tuple. But, you know, it's not one instruction, it's not hundreds of thousands of instructions. It's, yeah, you know, something like a predicate in approximately 100. Okay? All right, so now let's talk about disk. Okay, so does anybody know approximately how fast can you read from a spinning disk? About how many bytes per second can you read sequentially off of a spinning disk? Yeah. Yeah, so these modern disks are super dense, and in fact, you get the throughputs are quite high. Like 100 megabytes per second is not unheard of on a modern, you know, fast 10K or faster disk with the small platters. So these things are pretty, right? These things are spinning, and they're spinning really fast, and there's just a lot of bytes going underneath that head per second. They're spinning at, you know, 10,000 RPMs or something like that, right? And they're like, you know, so you've got a lot of revolutions, and the data is super dense. You've got, you know, a 4 terabyte disk, you've just got a lot of bytes going under that head per second. So you get quite a lot of throughput, actually. Like a modern disk will easily give you 100 megabytes per second. Okay? So 100 megabytes per second is actually pretty interesting if you think about it, right? Because this is 10 nanoseconds per byte. Okay? So that actually suggests that if you could read your data sequentially, like CPU and a single CPU and a single disk aren't that mismatched, right? You can kind of read data sequentially off of disk at about the rate that the CPU is going to be able to do anything interesting with it, right? Like if it takes me 100 nanoseconds to apply a filter, and you know, I can read, you know, a few bytes like an integer or a field or something in 100 in you know, a couple of tens of nanoseconds. You know, that suggests that these things are sort of reasonably matched. You know, they're not orders of magnitude off in terms of the rate of data coming out of disk versus it being filtered through CPU. So the place where disk really kills us, right, as you guys probably know, is in random I/O. Okay, so this disk is spinning around, right, at this 10K per second, but it's got this, you guys all remember this diagram, this thing is spinning, right, 10K per minute, per second, and there's this head that's reading on this, and this head can move in and out laterally, like this, and then it's spinning. And so if I want to get to a specific byte, like seek to a specific byte on this disk, does anybody know how long that takes? The seek time. A millisecond? Yeah, it's probably a little slower than the millisecond. I mean, the number that I've always used is 10 milliseconds, and maybe the disks are a little bit faster these days. I didn't actually look it up before the class. Does anybody think it's more like a millisecond than 10 milliseconds? Whichever it is, it doesn't really matter. Let's call it 10 milliseconds, okay? Okay, so to get to a specific byte, if I want to read a specific byte, instead of just if I'm reading data sequentially, right, it takes something like 10 milliseconds approximately, right? Which means that I can only do 100 seeks. Okay, so whereas here, you know, I could read these millions of records. I would be able to read these sort of 100 million records or bytes per second from this disk. If I have to look each one up randomly, I'm, you know, 6 orders of magnitude slower than that, right? Like if I'm just jumping all over the disk, right? So these, if I'm going to random places on the disk to find records, like if I'm following the leaves of a bee tree or something, and using rotational disk, it's gonna be a disaster. So you guys kind of see that? So this has changed a little bit. I mean, flash memory, flash drives have changed the world somewhat. Does anybody know what the seek times on a read times to read a random byte on flash disk are? What's that? It's better than a millisecond. I think it's like tens of microseconds. So it's to read a random byte. So it's still not quite at the sequential throughput, maybe. Like you can probably only get, say, randomly sequential throughput at, maybe 10 megs a second or something. But it's a lot closer to, sequential than random than disk. So flash, when you have workloads that are dominated by lots of little random I/O, can be a big improvement. This is why laptops all of a sudden boot 8 times faster than they used to, because it used to be that booting involved reading 8,000 little configuration files when the computer started up. You can read those 8,000 files now a lot faster than you used to be able to when your files are stored on a flash drive. Okay, so anyway, so this gives us kind of a ballpark. You might conclude from this that I/O is always going to dominate, right, because of this random I/O time. That's not exactly true, because well, first of all, we may be able to arrange things to be pretty sequential, and a lot of the sort of layout, data structure layout on disk stuff that we're going to talk about over the next couple of lectures is really about minimizing the amount of random I/O we have to do in order to answer queries that read lots of records. The other thing that database designers do, like people who are building big fancy database systems that want really good performance, is that they put a lot of disks into their computers. So if you go look on these benchmarks, like there are these database benchmarks, like GPCH is a classic database benchmark for doing what's known as analytic queries. So these are queries that read lots of data. And GPCH benchmark, the world record machine, has 528 300 gigabyte disks, okay? Why do you think it has 528, I mean, not the specific number 528, why does it have so many disks that are relatively small by, given that your laptop probably has a, terabyte or even 2 terabytes of disk in it? Why do you think they put these so many small disks in this machine? Yeah, basically to sort of advertise the seat cost, right? I have 500 disk heads instead of 1 disk head now, so when I have to do a seat, it's, I can cover that a lot, right? The second place machine has actually gone to flash. It's interesting this machine isn't flash. The second place machine has 144 4 terabyte drives and 96 800 gigabyte flash drives. So it has about 600 terabytes of total storage. This 600 terabytes of total storage is, or 700 terabytes. This incidentally is 700 terabytes of storage to do queries on a 10 terabyte base data set. Okay, so the machines that are trying to win world records are super over configured to be able to be really fast. But you can see that if, Flash has made a big difference. They have fewer of these drives than they did in this case, and they're almost as fast. So anyway. The sort of takeaway from this is, if we're not careful, random I/O is going to be really bad. In real world, oftentimes we can throw hardware at these problems to, hide some of the seat costs if we have to, but it's going to drive the cost of these up. These are like $1 million plus machines that people are using, which, you might be able to put together in some places, but most of them are going to be Okay, so what I want to do is, I want to, now that we sort of have thought a little bit about costs, I want to think a little bit about the total time to process some different queries. I'm going to use a bit of a simplified cost model here, just so that we can kind of, do some arithmetic on the board without getting overwhelmed with bookkeeping. So the cost model is going to be an I/O-only cost model. We're not going to focus on CPU time for now. We're just going to look at the cost to do the disk I/O. We're going to assume that we have a 10 millisecond seat, and we can read our disk at 100 megabytes per second. Okay, so this is cost model. Okay. And let's take a simplified database, our employees, departments, kids table. So we've got employees who work in departments and have kids. So we've got them and kids. Okay. And let's suppose that the size of depth is equal to 100 tuples. The size of M is equal to 10,000 tuples, 10K tuples, and the size of kids is equal to 30,000, okay? All right, so now in order to kind of work out this simplified example, we need a couple of other numbers. So let's suppose we can put 100 tuples on a disk page. Okay, so remember we're going to lay out this data in these pages like B trees or heap files. Let's assume we can fit 100 tuples of any of these tables on a page. And then we have a very tiny memory, so we have 10 pages of RAM to work with. Okay, this is obviously ridiculously simplified. And suppose that each page is 10 kilobytes per page. Okay, again, just some small round numbers to make this easy. Okay, so looking at this departments thing, we would say the departments table is 1 page. The employees table is 100 pages. Okay, and the kids table is 300 pages. Okay. All right, so now let's look at a SQL query. So let's take the following SQL query. Select star from depth kids, I'll write K, where salary is greater than 10K, E dot Dino is equal to D dot Dino, and E dot EID is equal to K. And so we're just going to do a very simple three-way join with a filter at the bottom. All right. So let's draw out a query plan for this. So let's suppose we first do when we're evaluating this, we first do the join between emps and depths and then join that with kids. Okay. So we've got join. We'll put depth over here in this diagram. We'll put the filter on salary with employees under here, and we'll join this with kids, and then we'll output it. Okay, so suppose this is the plan we're using. Let's suppose we're using a nested loops join, and a sequential scan here, and a sequential scan here. Okay. So this is a super simplified example. So let's just think about, so how many times this nested loops join, how many iterations am I going to do through this? How many times am I going to scan this inner relation? If the departments table is the outer, then how many times am I going to scan this inner thing? Okay, 100, right? Because there's 100 tuples that come up here, and for each of those 100, I'll scan this thing, right? And I'll scan for each of those 100 things, I'll read in 1,000. Okay? So I'm going to do 100,000 sort of predicate evaluations here in this nested loops join to do this join, right? Because 100 times 1,000, right? How many tuples are going to be on this edge? What's the size of the join output going to be? Do you think? I haven't actually given you enough information to tell this, but based on the sort of way I phrased the query, what do you think it's going to be? What's that? It's going to be 100? 1,000. Okay, so it's probably going to be 1,000. So why is it going to be 1,000? Yeah, okay, because probably DID is this E.DID, E.Dino equals D.Dino is a sort of foreign key reference from employees to departments, so we'll get one department for every employee, right? Everybody see that? I know that sometimes people are a little bit confused by that idea. Okay, so now we've got 1,000 of these vectors coming out here. We've got 30,000 kids, right? So the total number of evaluations here is going to be big, right? It's going to be 30 million, 1,000 times 30,000 total predicate evaluations to produce this output here, right? And then what's the size of the total output? Sorry, this number, right, actually, this number is going to be made out to be 1,000, right? It would be 1,000 if this predicate weren't here, but this predicate may reduce the number of employees who actually pass, right? So it's going to be some predicate evaluation of this, but it could be up to 1,000 records coming out. Yeah.
Are there 10,000 tuples for employees?
What's that?
Are there 10,000 tuples for employees?
Oh, good, thanks. Okay, thank you. Okay, so so this number should be. I wrote 10,000. Okay, so this number is 10,000. I'm sorry, this would be 10,000, which means if this were filtered, we would have 10,000 out here, right? Sorry, thank you for pointing that out. Okay, and then we're going to filter it. So whatever, we could say if this thing filtered out, all but 10% of the tuples, then we would say, we might have 1,000 edges, 1,000 here, and then we'd have 1,000 times 30,000 equals 1 million. Could filter more or less depending on how selective this predicate is. Okay, so this is the kind of and you can see it's fiddly, doing this sort of thing is kind of annoying, but this is the kind of thing that the query optimizer is going to have to do internally. It's going to have to kind of evaluate the sizes of these things, and then, based on the sizes of these things, compute the kind of optimal cost. So let's take just this example of this simple join here, okay? And let's just think about the simplest possible way of evaluating this join, which is to do it as clues. Okay, so case one, so let's call this join 1 here. Okay, so join 1. Okay, and case 1 is that D is outer. As I've drawn it here, so D is the outer of this arrow nested groups. So just considering this I/O model, how much time is that? So it's actually, you have to think about this a little bit. In order to figure this out, it's kind of like, you kind of need to think about the fact of how much RAM you have, right? So the case here, and the kind of interesting thing about this case here is that this employees table is 100 pages, and it doesn't fit into memory, right? So if for every one of these department tuples on the outside, I do a scan over this entire employees table, I'm not going to be able to cache the employees table in memory as I go through it. Right? The best I could do would be to cache 10% of the employees table, because that's how much space I have, right? At least 10 pages of memory. If we're using sort of an obvious cache management strategy, like an LRU, least recently used cache policy, where we evict the oldest thing that we put in cache. In fact, when this thing doesn't fit in memory, we're not going to be able to fit there's not going to be anything in the cache. We're never going to hit on the cache because we're going to have evicted the oldest thing. We're going to have evicted the thing that we needed by the time we get back onto it. You guys kind of see that? So the cost of this is going to be pretty bad, actually. It's pretty stupid, right? Like, we're going to scan this thing over and over and over again from disk. Okay? So we're going to do 100 scans, in fact, of E. Okay? And those 100 scans of E, well, each one is going to take, how long is each one going to take? So this thing is 100 pages, each page is 10 kilobytes, so call that a megabyte. So how long does it take? Okay, we can read, sorry, it's a little hard to see behind there. We can read 100 megabytes a second, so how long does it take? 10 milliseconds, thank you. Okay, so 10 milliseconds for each scan. Okay, probably we need to say that disk is going to have to seek back to the beginning of this thing after every time it scans it, right? So you have to do plus a seek for every time you access it, so plus 10 milliseconds per seek, okay, which is equal to 20 milliseconds per scan. Okay, we have to do 100 of those, so times 100 is about 2 seconds. Okay? Cool? And then you got to read this D thing. The D thing is just one page, so we probably have to do a seek to read it. It's super tiny, so we can read that 10 kilobytes in a tiny fraction of a second. So like, it's a little bit to access D, so plus 10 milliseconds. okay? To read D, D can fit in memory, so we can keep all of D in memory. So we don't even, it doesn't matter they can fit in memory. We're just gonna scan it once, pick up each D tuple, scan all of E, pick up the next D tuple, scan all of E, and so on and so forth. Okay? So this is kind of, it gives you a sense of the time you run in this strategy. So what if I reverse these? What if I put employees as the outer and these the inner? Yeah?
Before you go on to that, can you repeat what the 10 millisecond add-on?
Oh, I just have to read D once. I have to scan through D, and I have to, like, I read its one page into memory, right? So I had to do a seek to get to it. So this is D. I'll just put D under here, and this is the time. Yeah?
Do we have 100 scans of D?
Because I got 100 D tuples. Yeah? This cost model is a super simple cost model. We're not going to worry about CPU, RAM, access costs. All we're doing is worrying about just access costs in this case. I mean, we could have thrown in CPU access costs and said that, you know, the time to evaluate a predicate is like, you know, whatever. We said it's 100, you know, a predicate is 100 instructions. We might say, you know, 100 nanoseconds to evaluate a predicate or something. I mean, you could make this problem more complicated if you wanted to, but I can't do the arithmetic on the board already as it is, so I'll keep it like this. Okay? You have another question? So 0, yeah. Yep. Why is it 10 milliseconds for E? Oh, it's 10 milliseconds for D because D is one page, right? So we have to seek to the beginning of it, and then that time to read one page is like, it's 10 kilobytes over 100 megabytes per second, so it's, I don't know what it is, but not gonna help. A few, it's like less than a millisecond, right? Okay, so now back to the question I asked, which is what if I switch these two things around? What would happen?
It would be faster.
It would be faster, which is kind of surprising, actually. I mean, at least at some like simple level, it's kind of surprising because you're doing the same amount of CPU work, right? Whether I put one on the inner or the outer, it's still 100 times, you know, 1,000 predicate evaluations to evaluate this thing, right? It doesn't matter what order I multiply those two things together, I still get 100 times 1,000, right? So, or 10,000. So why is it faster? Yeah.
You can load the entire department thing into the RAM and then just like you don't have the looping.
Good. So D fits in memory, and because the inner fits into memory, it's a lot faster. Okay. So we can work it out, but I only have to read D once, right? So if I make D inner, right? Well, then I get, you know, I read. Basically, I can do something like read D into RAM, and then I can sequentially scan E. Okay, so I can read D into RAM. That takes me 10 milliseconds. Okay, and I can sequentially scan E, right? And E is 100. It is 1 megabyte. We already know the time to sequentially scan, and I can read 100 megabytes per second. So the time to do that is 10 milliseconds. Okay, so I went from, so the total here is 20 milliseconds. Okay, maybe I need another plus 10 milliseconds here to seek to the beginning of E or something. I might have missed one seek, but at some level, you can see that the runtime, we went from this, you know, 2.1 seconds to 20 milliseconds by reversing these things. Right, so actually, nested Loops join, it seems like a stupid join strategy. And it is quadratic in the runtime, but its I/O performance is not terrible when the inner fits into memory. And for very small tables, you'll actually sometimes see real query optimizers choosing nested loop joins for small tables when the small table can fit into rings. You guys see that? Cool. All right. Okay, so there's this thing I haven't really talked very much about, but you kind of saw here, which is like. I just said we've got some least recently used cache model. So the cache is actually kind of complicated. And so this cache in database systems is the buffer pool. You guys have implemented a very, very simple buffer pool for SimpleDB. And the buffer pool is sort of responsible for figuring out which pages it keeps in memory. In the SimpleDB exercise we've done so far, you haven't, I think, done any eviction at all. So you just loaded everything in memory and assumed that things fit and didn't worry about not having space. You'll have to add eviction later, and we'll do a couple of lectures we'll talk about how we can be a little bit smarter than using least recently used for all the data to be loaded in the buffer. Okay, so this buffer pool is sort of, as you've seen in SimpleDB already, is kind of the bottleneck through which all the accesses to data go. And that's going to turn out to be convenient later because not only will it be our sort of where we cache stuff, but it's also going to be how we manage concurrent access to data. So everybody who needs to read data will always ask the buffer pool for permissions to read data. And if there's somebody else concurrently accessing it, like locking it or something, then that other guy will be forced to wait. So the buffer pool is this sort of central data structure through which all data access to database systems can be used. Okay. All right, so what we're going to do now is we're going to talk a little bit, now that we kind of have a vague high-level sense of cost models, we're going to talk a little bit about costs of different access methods. So we're going to switch gears and start talking about access methods. So remember, access methods are sort of the way that we get at these base tables. Last time we talked about heap files, okay, which are just unordered collections of records. And we also briefly talked about B-trees, okay, which are these tree-structured indices that allow us to sort data according to some attribute. So you could see, in this plan or in any plan, oftentimes if we have an index that allows us to access the data, it's going to be kind of hugely beneficial. So let's just write down all the different access methods and things that we like, different varieties of access methods that we might want to think about. Okay, so we already saw heap files. I'm going to write a sort of parenthetical here, which is a sorted file. So we saw the notion that you could cluster a heap file, and you could imagine keeping this heap file sort of sorted in specific order. Actually, when we talk about column-oriented databases next time, we'll see that they employ sorted files. So a sorted file is sort of like a simplified version of an index, where the data is just stored in the heap file, but in a particular order in the heap file. Okay, and we'll talk about that more next time. And then we have indexes, and so the types of indexes that we can have are, we have a couple of different, we have clustered versus unclustered. We talked about last time this notion that you can have a B-tree sorted on a particular attribute. Again, we'll come back to that when we review B-trees a little bit. And then we have a bunch of different types of indexes. So we're going to talk primarily about two. First one we're going to talk about are hash index or hash files. And then we'll talk about what are known as B+ trees, which are a slight variant of B trees, and we'll just go into a little more detail about their features. And then I'll briefly mention what I assigned, one of the readings I assigned today, which I think is just a good data structure to know about, are R trees. And there's a lot of other data structures sort of like R trees. These are good for multi-dimensional data. All right, so we've seen heap files already. We've seen a little bit about clustered versus unclustered. And then today, mostly what we're going to talk about are these hash indices, and we'll briefly mention B trees and R trees either at the end of class today or next time. Okay, so with that little introduction, why don't we take a break, go ahead and take 5 minutes, we'll come back at 3:17, and here's a little thing from So like representing like those distinguished marks and then like some very All right, guys, let's go ahead and get started. Okay, so hopefully this, I didn't actually think very carefully about the answer to this. So if you think about these problems, so for the first one, if you want to think about the time to sequentially scan this grades thing, right? So if it has 1 million records, then in order to think about the time to sequentially scan it, we're going to want to think about how big the tuples in the grades table are. So how big do you think those tuples are? Well, how big is an integer?
4 bytes.
So it's probably 4 bytes. It might be 8 bytes, but it's probably 4 bytes. Okay, so we'd have 8 bytes plus 2 bytes, so that would be 10 bytes. Okay, so if we forgot for a second that there were a header on these tuples, then we would have 10 byte tuples, so we'd have 10 million records, so 10 megabytes, we do 100 megabytes a second, so that sounds like 100 milliseconds, right? Okay, so in reality, these tuples have some kind of header information on the front of them, right? Like they need some little directory thing that tells us where each field begins. In SimpleDB, we didn't have this because the fields are all fixed length. But if you go look at different implementations of database systems, the size of the headers are going to vary, but could very well have 10 bytes of header per tuple. So you might well have 20 bytes per record instead of 10 bytes, in which case it would take twice as long to scan this. Okay? Does that make sense? All right, so what about part 2? This one should be pretty easy, right? What should we do? What should our join strategy be? We're only doing nested loops. What should we put on the inner? Say it louder.
The one that fits in memory.
Students, right? So we put students on the inner, and then basically, like if we're only worried about I/O cost anyway, basically this whole thing is dominated by the cost to scan this larger, larger table on the outside. Yeah, the student space, millisecond or something to scan, right? Okay. So hopefully you guys would have been able to, if I put this on quiz, get it right. I hope. Okay. All right, so let's go back to our talking about heap files, etc. So we're going to do, we talked about heap files, we're going to talk about different types of indexes, and I want to, as we do this, build up a little table of costs. All right, so heap hash +3. Okay, so suppose we've got n records, p pages per file or index. So like if I talk about a heap file, it would have p pages, the hash would have p pages, etc. And then when we have a range predicate, the B-trees allow us to evaluate range predicates. Let's suppose we have r pages per range. Okay, so if we think about the cost, and now, sorry, I know this is like, I'm going to just move this to a different place on the board because I forgot to write what the rows of this table are. So we've got n records, p pages, and r pages in a range. Okay, so n records total, p pages in the entire file, and r pages in whatever range we're accessing. Okay, and now let's write down what the costs are to look up a tuple, scan the a range in the database, and delete it. Okay, so search is find one tuple, scan is scan through a range or a subset, and delete is to remove a tuple. Okay, so for a heap file, how long does it take me to look up a tuple? What do I have to do? I'm going to find a specific tuple. I got to read the whole damn thing, right? So it's like maybe and asymptotically or something, I only have to look at half of the thing because I get 50%. If I do enough scans, on average, I'll find it after going 50% of the way through it. So maybe a p over 2. And if I want to scan to find a bunch of tuples or to scan a range, I got to read the whole thing. So I have to read all p pages. And if I want to delete something, well, I got to scan. If I know the exact record ID I want to delete, I have to scan through half the file on average. Fine. Okay. So let's now talk about hash and B-trees a little bit and try to fill out the rest of this table. All right, so okay, so let's take the simple example of a hash file where all the records well, let's take the example of like an in-memory hash table. So suppose I want to store a table of employees hashed name. Okay, so if I wanted to store this hash table in memory, what would I do? Okay, in Python, what would you do to create a hash table, or whatever your programming language is? What would you do to create a hash table on name? I'd like iterate through all the records, and I'd put them in some, I'd say T sub, you know, R dot name equals R or something, right? I could just iterate through these and create a hash table in memory in my favorite programming language, assuming that this left bracket, right bracket notation means like, you know, index into a key by name, right? And R is my record, right? Okay, so what does your favorite programming language actually do when you write this tr.name thing? Like, how does it figure out what is it actually storing under the covers? Anybody know? Yeah?
What's this doing?
Okay, so it computes some function of this input, which is name, and that's called the hash function, right? And then it uses that lookup to figure out, you know, a cell in an array or in some data structure to store this in, right? So the hash function, this h of name, right, is a mapping into some key space 1 to k, right? And you know, choosing the right hash function is there's a lot of work that goes into choosing the right hash function, but a simple thing to do would be to take, you know, the input value mod k. So like x modulo k would take any input as, you know, represented as an integer and produce a value in the range 1 to k. People don't like this hash function because it has kind of bad skew properties sometimes, but this is a fine like way to conceptualize what a hash function is actually doing. So we get this number 1 to k, and we have some data structure, okay, which has k slots on it. Okay, and we would just write the records as we would just hash each of the records and write them into this data structure. So R1, you know, R2, R3, R4, R5, you know, et cetera, and so on and so forth. These records would just be populated into this data structure. Okay? And this data structure, typically we might call these you know, bins or something. Okay? Each of these bins is going to have a certain number of slots in them. Okay? So this is kind of the way an in-memory hash table works. What happens if we fill up the number of bins in one of these spaces, like if one of these things fills up? Well, there's a lot of things we might do. The simplest thing we might do would be to, you know, sort of have a pointer here to the next bin for this hash bucket, so that then when I want to look up a given record, I have to scan through this chain of bins that are there, but right? So the kind of nice thing about this data structure is that as long as I size the number of bins correctly, as long as I have the sort of approximately the right number of bins, I can get order 1 lookup time on this, right? I get asymptotically order 1 lookup time to find a given record in this hash table, right? But I didn't have to pre-allocate an array that had exactly the right number of cells in it for the data that I needed, right? So it's a super convenient and widely used data structure. We use it all the time. So we'd like to extend this kind of data structure to a database system. And the challenge in a database system is that, of course, this table may no longer fit in memory, right? So we want to have the ability to have this thing stored on disk, okay? So the trivial sort of naive thing we would do, or easy thing we do, is we would replace bins with pages, okay? So we would have page 1 through page k, that would be our hash table, right? And then we would, you know, when one of these pages fills up, we would somehow, you know, chain these hash tables together, right? So this would be an overflow page or something. Okay. All right, so just to sort of show you how this would work, we've got some data like this. We have this hash function. It will, you know, we'll pass each tuple through the hash function, and it tells us where this thing goes. Okay, so the sort of challenge is, and this is actually true in an in-memory hash table as well. You know, how did I pick this value k for my data set, right? So what happens if I make k like if k is much smaller than the number of like tuples that are in my database? Yeah.
You're going to get a lot of things to scan through.
Yeah, these, you know, each of these pages is going to have a lot of records in them. I'm going to have these long chains, and you know, in the worst case, this is going to be like, you know, a heap file, only worse because I'm going to have to follow these pointers. I'm going to have to like read large fractions of the database to find any any particular record that I want to find. Okay, and what happens if I make k like really big? So why don't I just make k like a billion and say, you know, a billion's got to be big enough?
Wasted space.
Yeah, I'm going to waste a bunch of space. I'm going to allocate all these pages on disk that I'm not really using, right? So what we'd like is some kind of something that can sort of allow us to dynamically size these hash tables. And actually, this idea can be used in an in-memory hash table as well. This is this idea of extensible hashing. And there are a couple of different variants of things that are sometimes called extensible hashing or extendable hashing that work kind of in a similar way. But the basic idea is that what we want to do is to dynamically resize this table as pages start to overflow. I mean, in fact, we're going to get rid of overflow pages entirely. So whenever a page overflows, we're going to resize the table. But we don't want that resize operation to require us to have to rehash every tuple that we've already inserted in the database, right? So like a trivial solution to this problem would be to say, as soon as a page overflows, you know, change my hash function to be x mod 2k, rehash all the tuples, and then you know, see, you know, then and reinsert them all in the database, and then I'm good, right? Until I overflow again. That would be a simple solution, but it's kind of ugly because I have to rehash everything. So we're going to see how we can do a little bit better. Okay, are there questions now? All right, so actually this idea of using this hash function, you know, doubling this value k over and over again, isn't a bad one. It turns out actually to be kind of a good idea. But what we need to do is to add one extra kind of level of indirection to our system to make it work. Okay, so we're going to define a family of hash functions. Okay, so if I have h of x in the range, say, produces a range from 0 to, say, b minus 1, okay, then, this board is terrible. Take that board. Right. Sorry, does not, it's 30 years old or something. Okay, h of x is equal to 1, 0 to b minus 1, okay? And then let's define h sub k of x to be h of x mod 2 to the k. Okay, so all this means is that, so h sub, the only values that h sub 1 can produce, for example, are h of x, you know, modulo 2, okay? So if k is equal to 1, then my hash function produces two values, 0 or 1, okay? So h of 1 produces something in the range, it produces something in the set 0 to 1, now h of 2 produces something in the set 0, 1, 2, 3, and so on and so forth, right? So I have this family of, sorry, I'm not getting my notation right. H sub 1, H sub 2. Yeah, I have this family of hash functions, H, that produces these values that get progressively larger. And now, there's this, what we're going to do is we're going to create this additional data structure, which we call a directory. And what the directory is going to do is it's going to tell us it's going to basically keep track of the kind of k value for each one of these, for each record that we're looking at. So let me just show you how it works. Okay, so we create this family of hash functions. We're going to initially set this k to be 1. And we're going to create this directory structure that keeps track of the mappings from hash values to pages. Okay? So this directory is basically going to say that if the hash value is 0, it should go to a given page. If the hash value is 1, it should go to some other page. Okay? And it'll look something like this. Okay? So here's our directory. So it says hash 0 maps to page 0, hash 1 maps to page 1. And we've got our page table, which was just the structure we had before with its page contents. So at this point, this looks pretty stupid, right? Like, why did I introduce this directory? So now let's just look at an example and you guys will immediately get the idea. Okay, so we're going to start off with page number 1. We insert these records 0, 0, 2, 3, 2. Okay, so we hash the first record 0, it goes into that page. Second record also goes into that page. Now we hash 2, it also goes into that page because 2, 2 modulo 2, right, is equal to 0, right? So if the hash value of this record was 2, then 2 modulo 2 is going to go into this 0 bucket, right? Okay, but now, and now the next record comes along, 3 modulo 2 is 1, we put it in there. Okay, so now comes the trick. So we overflowed this page at this point, right? We have another 2 that we're about to insert, right? So what's going to happen is we're going to actually extend the directory to include, we're going to increment k, and then we're going to extend the directory to include these new pages. So when we increment k, we'll have 4 possible hash values that we can produce, 0, 1, 2, or 3, okay? We'll increment k and we'll create these new hash values. And then, what we have to do is we have to rehash the values in the pages that we split, right? Or the page that overflows. So we'll rehash the values in this page number 0, but we don't need to rehash the whole table. Okay? So in particular, what we'll do is we'll allocate this new page, page number 2, to hold the values of the overflowed tuples. Because we know that these things that are in page number 0, right, if you think about what buckets they could end up in when we rehash them according to this new hash function with a larger k value, they can only end up in bucket 0 or in bucket number 2, right? Because previously they hashed to bucket 0. The only other bucket they could possibly hash to when we increase the hash value is bucket number 2. You guys see that? So we only have to worry about rehashing those tuples that are in bucket 0. So we rehash those tuples, we allocate this new page, we'll come back to this point in a second. We rehash all those tuples, and we'll find that when we rehash all those tuples, only this tuple 2 ends up in the new page. Okay? And then there's a final little trick, right, which is that I didn't actually have to allocate a new page for this page number 1, right? That page didn't overflow, so I didn't even really need to waste the space on disk for this. I just put an entry into my directory that says, well, if you hash to value 3, actually you should still put values on page number 1 because you didn't need this, like we didn't need to allocate this extra page at this point, right? So we only need to allocate additional pages when things actually overflow. All right, and there's a little bit of bookkeeping that we need to do to keep track of when we should increment k, right? Because in this case, if bucket number 0 overflows again, we would need to increment k again, right? But if bucket number 1 overflows, we actually don't need to increment k because we've already extended the hash table to have this entry for 3. Yeah?
So what would happen if you had a bunch of 3s so that the 3 row, like the 1 row overflowed, and then when you add it to 2, it wouldn't really help me?
Okay, good. So a problem with this data structure is that if we have the same value over and over and over and over again, which may sound crazy, but there definitely are databases, right, where like 99% of the records have this some value, like 0, right? So you could get into situations like that. So you need to kind of do something to deal with this, right? Either you could add overflow pages, would be a sort of trivial thing to do. They say recognize that you might never be able to deal with. You might still have to have overflow pages for large numbers of duplicate values, or you could have a slightly more complicated family of hash functions such that this might not happen. Like you could use some other hash function on those 3 values that would cause some of them to go into a different place. But dealing with this is tricky. Dealing with large numbers of overflows is pretty large numbers of duplicate records is going to make, as a case where hashing doesn't work very well. Hashing is not good when you have lots and lots and lots of the same value. I'll try and figure out what the standard practice is for how people deal with this in hash indexes. There probably is some solution that people use. I'll go look and see what. I'm not 100% sure what most implementations do to deal with this situation. Okay, other questions about this? So it's just kind of a cute trick. Yeah.
So rehashing doesn't mean that all the existing entries have to be changed. The existing entries remain in the same space.
Yeah, basically all we would do is we would walk through the page, read a tuple, apply the hash function to it, and if the hash function said that the hash function with the new k value if the hash function said this tuple should go into a new page, then we would delete it from this page and write it into the page into the new page that it was supposed to go in. So we have to move all the tuples whose hash value changed as a result of incrementing this.
All that other things is attached to the bucket. So that the two values have the same hash function, I put it in a linked list. What happens with that linked list once I get it in hash?
So, all of these data structures have these issues, like we're talking about the heap files, where you can have spacey gaps in the middle of them. And anytime you're doing this kind of data layout stuff, you have to have a strategy for dealing with those holes or gaps, right? So, in this particular implementation, so if all the records are the same length, right, this isn't so big a deal because we just keep track of where the empty holes are, and then eventually we'll stick some more data in there and it'll fill out those empty holes. Right? Does that kind of make sense? The challenge is when the holes are different, when the tuples are different sizes, then you'll end up with this kind of fragmentation where you'll have holes of different sizes kind of floating around in free space that's not used. And that requires some sort of a compaction implementation. The way that this data structure is typically going to be implemented is that this heap file, this hash file, right, which has this list of records in it, so this is our hash, there's going to be a heap file over here. And what we're actually storing in this hash, just like in B-trees, are pointers, not the records themselves, right? So they're going to have hash values and pointers, right? And so we'll have some fixed number of slots, but every page will have the same number of slots, and each slot will be the same length. And these will actually be pointers into this heap file over here, okay? And so this kind of compaction thing probably won't be too big of a deal in this particular case. We have to deal with this compaction thing in the heap files, and that's the place where this sort of space reclamation and having to move stuff around is going to matter. Yeah?
So if you had like the row that's not the number one row, that was like 313, and then it got full, but there's also in the top row 002. Would you need to rehash every single thing?
So you're saying that this was 313,
Yeah.
and then we tried to insert a new record in there?
And top row is 002, so top row has a 2 in it. So
Yeah.
when you fill up one of the rows, then you add the 2 row, which now the 2 from the top row should go in the third row.
Okay, it shouldn't, right? Because what's going to happen is this page number, the things that previously hashed to page number 1, right? When we go to this new hash function, are going to all hash. They're not going to hash to bucket 2. They're going to hash to bucket 3, right? And this 002, well, this page, if that page hadn't overflown yet, like we didn't need to create the space, then we wouldn't have created this entry for 2, right? We would have made page number 2 would confusingly have, a little bit of confusing, but the entry would actually say h sub k of x is 3 and page number is 2, right? And then when the above page overflowed, we would add a new entry which would say h sub k of x is 2 and page number is 3, right? So we have this directory which maps between hash value and page number, but it's not like page number 2. It's not that hash value 2 always has to map to page number 2, right? Hash value 2 can map to page 27.
So when you insert a record with key, what's the meaning of like the same key but different value? But you said that you can have the
Okay, good. These are tuples, right? These represent a entry in the database. So I could have, the question was, why are there tuples with the same key, but in this database, right? These are tuples, right? This is a hash function. So these might be, I might be hashing on employee name, right? So I might have 2 employees named Bob Smith in my database. That may be perfectly reasonable. So those 2 employees are going to have exactly the same value, hash value, and they're going to map to the same page, but they're different records. And I need to keep track of the fact that they're different records because, when I do a select count star where name is equal to Bob Smith, I better get 2 and not 1, right? Okay. Other questions? All right, so now we're gonna, so if we think about hashes, so hashes are pretty cool. They get this property that we can do lookups in order one time, equality lookups in order one time, okay? So that means like I read 1 page on average, right? I have to go through this directory structure, hopefully the directory structure is in memory, and I just go look at the page, and hopefully there's not some big overflow. I can also do deletes in order one time, okay? The bad thing about these is that, well, I can't do scans at all. I can't, unless I can enumerate all the values in a given range, I don't have any way to use this hash function to like scan a range of things. So if I want to say, find all the employees who make between $50,000 and $60,000, right? Unless I could somehow, I mean, I guess I could walk through all the dollar, if I know that I only make, I have non-fractional salaries, could walk through all the dollars between 50,000 and 60,000 and do 10,000 lookups on the hash table. But, that's probably not a very good way to answer that query. There's no way to like find all the things in a range because the records in that, the records that correspond to the salary of $50,000 are going to be in a totally different bucket, maybe, than the records that correspond to the salaries that are $50,001. There's no kind of locality in these hash structures, and so there's no real way to do scans. So they're great because they're kind of they're order one time to do lookups, but not so good because we can't do scans, right? So what trees buy us basically is logarithmic time performance to do lookups, scans, and deletes, right? Yeah, question?
So in the hash keys,
Yeah.
I mean, the records is the stores them now, but you just like iterate over.
Sorry, you could sequentially scan. I guess you could sequentially scan the hash table. Is that what you're saying? Yeah, you could scan the hash table, and it's possible that that might be more efficient than sequentially scanning the heap file because the hash table is like smaller than the heap file itself, right? So you could maybe get some performance gain out of doing this. I don't know whether database systems implement, any database system implements this. They probably do, and it's like sometimes it's going to bite. Okay, all right, so B-trees have this, what B-trees get us is kind of this logarithmic performance to do search, scans, and deletes, just like, any sort of tree structured search algorithm or sort algorithm you've seen before. So let's look at kind of what B-trees, let's draw a conceptual diagram of what B-trees are. In particular, I want to talk about these B+ trees. Okay, so a B+ tree, you remember last time we talked about the nodes of these B trees? So we talked about there being inner and leaf nodes. Okay, so what these inner nodes look like is sort of a pointer, and then a value, and then a pointer, and then a value, right? So these pointers, I'll shade these pointers. Okay, these pointers are sort of pointers to subnodes in the tree, and the values define the boundaries. So everything less than this first value, val1 here, would be over here in this subtree, right? And we have this kind of structure where we've got val, pointer, and so on, right? So everything less than, sorry, I did it back. Pointer, value, everything less than this value, again, would be over here. And then at the bottom, we have these leaf nodes. Okay, and we talked about how last time leaf nodes, what leaf nodes have in them are values, and then they have a special kind of a pointer into the heap file, right? We're going to call these heap file pointers, they have these value heap file pointer things, and we'll call these heap files RIDs. RID is a RID is a record identifier. Okay, and the reason we're calling it a record identifier instead of just a pointer is that, well, this record in the heap file may not actually be in memory. It's like some location on disk. So we need some sort of way to identify it. And typically we identify it as like the page number and in the heap file and the tuple offset into the heap file that we need to go to look this thing up. Okay, so these leaf pages are going to have val rid pairs in them, like this. Okay. Now, so this hopefully this is what we talked about last time. Hopefully this isn't a surprise. It's just a sort of pretty standard way to lay this stuff out. If you think about, so we'll often draw these diagrams that look like this with these pages hanging off of them. So these are the inner pages. So let's not worry about the inner pages right now. This is just a sort of graphical representation of an index. You often will see these pictures that kind of look like this. Okay, and these are the leaf pages. In these B+ trees, these so-called B+ trees, the big difference between them and B trees that you may have seen before is that they have these pointers that chain the leaf nodes together. Okay, so the thing to sort of observe about the leaf nodes of the B tree is that they are in sorted order according to leaves. So if I walk from this leaf node to this one, I can navigate through the pages, the records in sorted order. So if I want to do a scan, I can just jump from one page to the next. The other thing about B plus trees is that they don't store these record IDs in the leaf pages. You could imagine a B tree structure where I stored these record IDs in the leaf pages. So in the inner pages, the record IDs are only stored in the leaf pages. So these values are just the sort of ranges of the records that are underneath this subtree, but they're not the actual, they don't have actual pointers. This is a little bit different probably than some of the tree structures you may have seen before, where you commonly will sort of store the actual values or actual records themselves inside the inner nodes as well. All right, so this is a B plus tree, and it is, again, it's differentiated from a conventional B tree by inner has no data grids, just the ranges, and it has these next child pointers. Okay, all right. Okay, so these B trees have some relevant properties which we should talk about. Okay. So the first one is what I call fill factor. And so do you think these pages are, so is it a good idea to have every page in this data structure be completely full with tuples? Okay, so what's good about having every page in this data structure be completely full of tuples? Like having, like if every one of these leaves have a certain number of, they're like, 4 kilobytes big, and maybe values are 4 bytes and grids are 8 bytes, so I can fit like, 4K over 8 records in each one of these leaves. Should I pack every one of those leaves full of records? So what's good about packing full of records?
Let's go back to when you want to insert things.
So these, remember so you said it's compact, but if you want to insert, it's bad, right? So the challenge with, the advantage of these B trees is it's supposed to be, insertions should be sort of logarithmic time. But the problem is that if every page is full, then an insertion is going to require me to do this sort of rebalancing thing where I split pages, and it's going to be slow. So the fill factor is, how is the occupancy of the pages. And in B trees, typically the fill factor is always greater than 50%, but you might sometimes make it less than 100%, right? You would only make it 100% if you thought you were never going to add data to the B tree, right? Okay, so that's one thing. The other property of these B trees, of course, is that they're balanced. Again, that's important because we want logarithmic time lookup. So if these things, had some big skew to them, we'd be in trouble. There are these rebalancing algorithms that are in the readings that I assigned to you. Again, I'm not going to go through the gory details of how we, do insertions and rotations on these B trees to maintain the balanced structure. Hopefully, you guys have seen this kind of rotation business at some point in the past. If you haven't, have a look at the readings. Again, it's kind of fiddly, but it's, all these structures sort of do something similar to rebalance themselves. And actually, you'll get a chance to do a partial implementation of this in SimpleDB, so you'll know it very well. Okay, so let's think a little bit, and the last point I want to talk about is just like how many levels. Okay, so suppose I've got 4K pages and 8 bytes per entry, which implies 512 entries per page. Okay? So that means that the branching factor of this tree is like 512, right? Do you guys all see that? So B in that sense is 512, so the log, so this structure is going to grow with log base 512 of the number of records. So how many levels do you think this typical B tree is going to have? Well, if I have one level, I can store, 1 plus a level of leaves. I guess I can store, 512 squared values in a root node with 512 leaf pages underneath it, right? So as I add levels, I kind of go 512 squared, 512 cubed, and so on and so forth, right? So this thing grows really, really, really fast, right? So like 512 to the fourth is 68 billion. Okay, so I can store 68 billion records. If these things are really only 8 bytes each, I can store 68 billion records in a level 4 B tree. So that means these B trees are really shallow, right? It would be uncommon to have a B tree of greater than depth 5. You might have keys bigger than this, but you'd be uncommon to have a tree of depth 5. And furthermore, the top levels of it are really, really small, right? The total number of pages in the top levels are B times less than are equal to the number of pages in the entire leaf, right? It grows in the number of leaf pages in total. So the top level of these trees can often be kept in memory. So even though the search time is going to be log base B of the number of records, each of these is going to be log base B of the number of records. Oftentimes, these times are better in terms of number of pages you have to read in log base B because of caching. We can store the top levels of the tree. Okay, so that's all I want to say about B trees. We'll kind of do a recap of this next time, and then we'll talk about column stores in a little bit more detail. See you next time. Good luck with the lab.